This is why a keyboard works, you know. So it's all the electricity in a sense. Now, this is about resistivity. I have put many things in here, of course, but this is just a picture reminding you and showing us something about the magnetic field, and in particular about the magnetic field lines. Again, you can ask the same question: how do I measure a magnetic field? So how? And the first question you can ask is there a magnetic field in this classroom, in this lecture theatre, more than a classroom? Well, you can use a compass, a small test compass needle, right? Magnetic needle, and look at the orientation of the compass. If the orientation is not the same as the orientation it usually has in the magnetic field of the Earth, then you know that there's an additional magnetic field present. And you can define the magnetic field lines according to the direction, the tangential direction again, this time of the needle, the compass needle. One important thing is that, what do you notice here, especially on the left? The magnetic field lines of a magnetic field are closed curves. The electric field can be different. A positive electric charge generates divergent, infinite if you want, divergent electric field lines. For some strange fundamental reason, on the other hand, the magnetic field lines of a magnetic field are always closed curves. They are not diverging like the lines of an electric field. So it's very different. It seems to be, again, very different when compared to the electric field, isn't it? So, right. This is about another question which you might remember somehow from your studies or readings and so forth. What is the origin of the magnetic field of a magnet, of a material magnet, right? A magnetized object or something. It's related to the spin of the particles which are inside this material. It's related to the spin, especially if you speak about metallic type of magnetic bodies. It's related really to the orientation of the spin of, or spin means also magnetic moment, little magnetic moment of the individual electrons, because the electrons in metal, you see, they are very delocalized. They behave in a very delocalized way. They are not around each atomic nucleus. So you can neglect the atomic orbital magnetic moment, but you can explain the magnetic properties if you look at the individual magnetic moment, which is linked to the spin property of the electron that the individual electron has. It is as if the electron were a small microscopic magnet with its direction and orientation. If all the spins of these electrons are more or less parallelly oriented, then there is a macroscopic magnetic field in the material. If the spins of the electrons are random, then the net magnetic field does not exist, you see, macroscopically speaking. And the theoretical explanation, therefore, of the origin of the magnetic field of magnetite or of magnet, a material magnet, is in reality very, very complex, very deep. You have to link ultimately the question to the spin, which you know, of course, will be a quantum number. But it's not just a quantum number. The origin, the ultimate justification of spin comes from a theory called relativistic quantum field theory. And that stuff is the union, and unification in a sense of quantum mechanics, and Einstein's special relativity theory. That is relativity quantum theory. Only in there you can really see, well, I need spin properties. Particles have the spin, you can have the spin property, like the spin of the electrons and so forth. It's not just something that you have to add on top of your theory to explain atomic models and the periodic table. So it's a very interesting thing. Spin is not just quantum mechanics, spin exists because of Einstein's relativity and quantum mechanics. It's the union of both. And all the technologies which exploit and which use the orientation of spin of particles in materials are technologically speaking very vast. Okay? There are many applications. In some books and treatises, all this is called not just electronics, but it's called in red there, you see, spintronics. Your magnetic bank card is just something that is possible because the reader can detect the orientation of the spin of the particles in your bank code card, in your stripe. See, that's an example, and so forth, and so forth, and so forth, and so forth. Nuclear magnetic resonance is all about spin orientation of particles, and so forth. And the response of this to magnetic fields. And here we are arriving to the conclusion of all this, if you want, slowly. And that is simply, you might have got the impression that electricity is one thing, magnetism is another thing, right? Both are fields and things. And however, the experiment of Ørsted shows that electricity and magnetism are related for the first time. Ørsted has, in his famous experiment, shown that an electric current, in this case a rectilinear piece of wire with electric current, carrying electric current, generates around it a magnetic vortex, if you want, a magnetic field whose field lines are concentric circles and so forth, in a perpendicular plane and so forth. So I have to remind you of another thing. Yes, the mathematical expression for the intensity of a magnetic field generated at a certain distance from a wire carrying carrying an electric current is due to Biot and Savart, two French physicists. Don't worry about the mathematics. But here we have another absolutely wonderful thing, okay, due to Michael Faraday. Let me remind you that Michael Faraday was not originally a professional physicist. He was the son of a bookbinder in London. He was working in libraries and was an autodidact in physics, just by passion. And Michael Faraday was a wonderful experimental person. He was very good with doing things with his hands, you see. He was not a theoretical person, not like Maxwell, okay, but he was able to imagine and devise and practically realize wonderfully ingenious and fantastic experiments. Right? He made lots of drawings. He didn't know mathematics very well. He didn't know theoretical physics very well. But he did he did draw and represent the results of all his experiments and try to publish them and so forth. And at first, what this person found was absolutely not taken seriously by the academic community in London and in what's considered to be, well, who is this person, what drawings, and all these curly, strange lines. You see, that attitude is maybe linked to the fact that, especially in England, everything was believed to be Newtonian mechanics. It's all Newton, right? This is all very non-Newtonian, of course, especially the structure of the field lines. And this experiment shows that there exists a magnetic force acting on portions of wire carrying electric currents. Okay? If you put an electric current in a magnetic field, it will undergo this famous force, F, linked to the intensity of the electric current and the intensity of the magnetic field. And this equation and this experiment is the answer to our famous question: how do I measure the intensity of a magnetic field, at least in this way? How do I define B, the magnetic field? Well, if the electric current is perpendicular to the direction of the magnetic field, this formula simplifies very simply. It means F equals Bill. F equals Bill means B times I times L. There's no angle, there's no vector product. If I look at the modulus, okay, the absolute value of the vector, the length of the vector F. So if F equals I times L times B, then B equals F over I times L, F over I times L, that means that B is expressed in terms of newtons over ampere over meter, times meter. So you can define the Tesla, this is called a Tesla. 1 Tesla is 1 Newton over 1 ampere times 1 meter, something like that. You define, and you can measure I, you can measure the length L, you know, you could measure the force again by that with a dynamometer, something like that. And you can measure B. And of course you might ask, well, how am I measuring I exactly, the electric current? It's slightly ambiguous. Well, this is another thing. This is a consequence of F equals Bill, if you want. On an individual electric charge, you have a Lorentz force. So when an electric charge is moving, it gets deviated, not accelerated, just deviated. It just changes direction by the action of the magnetic field. This is very important because this is the basic mechanism which allows you to construct particle accelerators, because if you want the particles in particle accelerators to acquire very high speeds, you must organize yourself in order for the trajectory to be circular or curved. And so you deviate the particles by magnetic field, so you use the Lorentz force. And so you need to construct very intense magnetic fields. That's a very difficult, of course, technological problem, but this is the basics of it. This is another experiment always related to producing magnetic fields through electricity without magnets. You have an electric charge rotating with a certain angular speed and linear speed, and you generate a central magnetic field. This is Rowland experiment. And the value of the magnetic field is proportional to the speed, the linear speed of the rotating charge. This is very particular. This is the magnetic field generated by coils, coil wire, coils, a curled wire or a coil, and by a solenoid, as you know. All these things in similar ways produce, when they are carrying electric current, they mysteriously produce a magnetic field. So what I wanted to say about the ampere is this experiment, the third one. We have mentioned Ørsted, Faraday, and now ampere. In this experiment, as you know, it is shown that two wires carrying electric currents are attracting each other or repelling each other. And this force is explained by the Ørsted experiment and by the Faraday experiment. It's a combination of both. But the wonderful thing is that this formula. I have a pointer. This formula here, you see, is British pointer. This formula here is, you see, a wonderful thing, because you have a quantity which I just called electric current, so ampere. How am I measuring amperes? Well, ampere is related to the distance, another distance, and a force. So if you play around with that, you can measure and define the ampere in terms of more fundamental thing, because otherwise you always have this Coulomb around. Right. Yeah, this is Ampere's law, again, a generalization. Just bear a moment, I just want to show you. So, oh, yes, of course. Now this is the other story. We've been speaking about electricity generating magnetism. This is the final part of the story. This is magnetism generating electricity. So you can generate electric currents, if you want, without battery or generators. You just have to vary, as it will turn out, the flux of the magnetic field defined in the same way as the flux of the electric field through a surface linked to the circuit